All right, so let's see, we're missing under Spencer. Okay, so we had problem one was the spring problem. Okay, so any concerns on that one? What the answer come out to be? I can't. What'd you have? 10 pounds of force it took to move the thing how far? The natural length is 18. Compress it to 6. It doesn't matter if you compress or stretch, it's the same. You don't use negatives or anything. So that's a 2. A 2 goes there. So K becomes 5. So that gives you your force equation of 5x. And so that goes in here. And then you're going to stretch it from that 16 down to 12. So what'd you put in on the interval? 2 to 6. Because when it's 16, it's already been compressed 2. And when it goes down to 12, it's been compressed from 18 to 12. That's a compression of 6. So these numbers are the compression. And then whatever that came out to be is what you want to have. So that is your, and there's really not another way to do a spring problem. You're going to have to be given some information about how much force it takes to compress or stretch it a certain distance so you can find what K is, the spring constant. Then you put that into your integral, the Kx equation, and then you have to figure out from what to what, and really that's as simple as it's going to be. Rope in a bucket. Now, when you get to number 12, a few people ask about this one on number 12 because they kind of combined the water in the bucket. All right, let's talk about 12 here. They combined the water in the bucket. They said what? When it started, it was 80 pounds. And when you got it all the way up, it was 40 pounds. And it was 75 feet of rope, and it was 0.65 pounds per foot. Right? All right, so how are we going to set this up? Let's deal with the bucket first. Anybody want to talk us through what... we talked a couple different ways on this one.
So changed 40 pounds, you would have changed 40 pounds per 75 feet.
Okay, so 45 pounds over 75 feet. Now you can think of that as a slope kind of thing. That was one way we wrote it yesterday. We said at 0 feet it was 80 pounds. At 75 feet it's 40 pounds. But you don't have to. You can do it as a slope formula. Think of that as a negative. That'd be fine. Okay, go ahead.
That simplifies to 8 over 15.
Okay.
And then you have to make an equation out of it.
All right.
So you have 8 over 15 times 75.
Okay, so one way we talked about doing it yesterday is doing it that way. Okay, because what you're talking about there is 8/15 pounds per foot of water is in the bucket times that is leaking out of the bucket and times how much rope is left. Okay, and so that's feet. So pounds per foot times feet. So at any given time, this would tell you how many pounds. But I think we're missing something there, aren't we? Well, I wouldn't need a negative on that. So, Miranda, tell me what the rest of your integral had. So you had that for the bucket?
Yep, and then plus 0.65.
So let's talk about the rope a second. So 0.65 pounds per foot. And then you had those two things in your integral? We're missing one thing. Well, I think we would need a plus 40. Now, Shelby, you're saying plus 80. Did you have this and then a plus 80?
Yeah.
Or did you have this written a little differently? Huh?
I had it like negative 8 over 15.
Negative 8 over 15
Yeah,
times x or times this quantity? Then that would work. Well, no. See, the 8 over, okay, the 8 over 15 is going to become negative when it distributes here. You see what I mean? So if we do this, let me think of the best. Try to explain this so it be least confusing. Robbie, go ahead. You said plus 40, right? Robbie,
Yeah.
So tell me why you had that.
When my equation, I just, for the weight of the bucket, I did 80 minus 8/15 x. And if you distribute that 8/15 through, that will go to 40 minus.
Right here.
Yeah.
Yeah, okay. There were two ways I talked about yesterday doing the bucket. Is if you do it like an ordered pair, right? And you say, okay, you had 0 feet of rope pulled in, there's 80 pounds, 75 feet of rope pulled in, there's 40. When you do your slope there, it comes up to negative 8/15. So I said that you could write that as just an equation. You could write that as negative 8/15 x plus the pounds you started with, which is 80. So your equation could be that. Okay? So that is the pounds. Now, because here's what has to happen. Here's the way you have to think about it. When you put a 0 in for x, 0 pounds pulled up, you need to have 80. When you have 75 pounds, you need to get 40, right? So when you put 75 in here, those cancel, you get 5, you get negative 40 plus 80, which is 40. So that comes out to be 40. The problem with this one here is if I put a 0 into here, I get 75 times 8/15, which is 40, not 80. You see what I mean? And now if I put a 75 in there, I get, and if I put a 75 in here, I get 0, not 40. Does that make sense? So I would need to have a plus 40 on that if I was going to set that up. Okay? Now I'm trying to think of a good way to, Shelby, you said you had negative on the 8/15, and yes, we're losing water, so it makes sense that we would have a negative on there. But if you set it up this way, that's going to take care of itself because of that negative that's in there. Yeah. Okay? So this one, I think on the rope, guys, the rope, every problem I would ever give you and I've ever seen on the bucket problems, this is going to be a great way to set up the amount of rope. It weighs this many pounds per foot, and this is how much rope is left. So that is going to be a great way to set it up. This is a little bit problematic on the water in the bucket because it starts with 80 pounds and ends with 40. It might not end with 0, and if that's the case, then you're going to have to adjust it by adding a little something on here. Okay, now, some people in the other class mentioned that in our notes, we had 3 things: bucket, rope, and water. In this problem, bucket and water were together, right? They didn't separate. Did they tell you how much the bucket weighed? They didn't, right? Now, somebody in this problem said, well, they took matters into their own hands. They just assumed that when the bucket got to the top and it weighed 40, they just assumed that to be the bucket. The problem didn't say it was empty, right, when it got up there, but it just said it weighed 40. So they said, well, I'm just going to assume that's the bucket. So what they did is they put the 40, so if you look at our notes here, right, bucket, rope, water. So what they did is they put 40 for the bucket. And maybe you did that, Shelby, I don't know.
If you make 8/15 negative and put an 80 out in front, you get the same as if you make it positive and add 40 to it.
Except if the 8/15 is negative times that negative, wouldn't that turn positive then? That's the one
Because I typed it in and I got the same.
you did. As what you had gotten the other way?
As
Or
if you did 40 plus a positive 8/15.
oh, okay, so you're saying an 80 here,
Yeah.
and that's what you have.
Mhm.
And a
then
negative
that-
here,
And the rope stays the same,
right?
and you stay at 66,000.
Yeah, but to me, if you have the negative there when you distribute, that would turn positive, where in this one it would. If you, right, so if you did 80 minus 8/15,
Okay. Yeah, I can see that.
you see what I'm saying?
I see how it works because it just be like if you distribute the 8.
So this becomes 80 minus 40,
Yeah, the 40 is just like
but then this becomes plus 8/15.
yeah, at 0 it would be 40 plus the 0.
so at 0 we would get 40, and at 75 we would get 80. I see. Because that would be, huh? Yeah, I see what you're saying there. Yeah. So when you put it into the integral, though, would that turn out negative? So if you did them as, but you did it as one big integral, Shelby,
Yeah.
with all of it, and you got
All
this
3 parts.
with all those parts. But you didn't have this third part over here, or did?
That was the 80.
That was the 80. That was that 80.
Yeah.
Okay. All right.
Stop running on physics.
Yeah.
I don't know. This is how I did it. And it worked.
But what I'm thinking is, wouldn't that be negative then?
Well, I think, doesn't that depend on what you call, like what X?
Well, right. Yeah. So in other words, by having those backwards, x instead of being how much you pulled up, it's how much is left, right? So at 0, how much is left is when it's all the way up. And so at 0 on this one, there's 40, right? And so that depends what x was. But if you do that here, then x is something different, right? But you had a negative on this probably then.
No, I had it positive.
See, because that's what bothers me in when you add the two together. Because in this way, x is how much rope is left. In this one, x is how much rope is pulled up, right? So that's why it seems strange that those come out the same.
Yeah, it,
All right. Okay. I can't move on until we fix it. So the integral went 0 to 75. So you're saying you had 80 minus 8/5, 8/15 times 75 minus x plus 0.65, 75 minus x, right? I'm saying it maybe should have been 40 plus 8/15 times 75 minus x plus 0.65 times 75 minus x. Okay, can we verify that those come out the same? Did you have them both, huh? Good. Yeah, and well, because how did we say this simplified? We said this would simplify to 80 minus 8/15 x. And we said this would simplify to 40 plus 8/15 x. Right? Yeah, well, think about it as an area. These two are obviously going to be the same. So this one, 40 plus 8/15 x, would be a piece of area like so. And this one here would be 80, so it would be up here, but then it would come down. And that would be a piece of area like so. Does it make sense that those would be the same? Right? This would start up twice as high, but then it would come down as opposed to go up. And so would those two have the same area. Yeah. So let's think about it in terms of pounds. That's just strange though, because the x means two different things.
Well, what's the equation for the other way to think about the rope?
Well, the other way to think about the rope would have been just how this one simplifies. The other way to think about the rope would have been negative 8/15 x. Wow.
Fool.
Oh, wait, no, wait, this is mine. No, that's good. Yeah, this is mine. Yeah, where you make the 8/15 negative. Mine.
This is like me and Shelby.
No, I like it. I like what you were thinking of. It just, that, okay. So negative 8/15 is you're losing the water, and then plus the 80 because that's what you started
I'm
with.
so glad you're recording this.
Yeah. Yeah, this would have been the other way. See, the reason I did like this is because when I first wrote that, then I checked it. When I first wrote that for the water, just like we do the rope, I thought, wait a minute, I don't think that's right because if x is 75, this comes out to be 0, and it's supposed to come out to be 40, right? Because when we get to the end, when we pulled up all 75 feet of rope, we should have 40 pounds of water and bucket left, but then that says we have 0. That's why I knew I had to add on a 40. Now, like I said, somebody in the other class, they set it up this way thinking it was two separate things. They thought of the 40, like the one we did yesterday, right? We had the 5-pound bucket. So they said, hey, when it gets to the end, it weighs 40 pounds. They just assumed it's empty and called that the bucket. So they said, here's the bucket, it's 40, and then this is 40 pounds of water when it started and none when it ended. And so they set it up this way, and so it worked out. But no, we didn't come up with this one, but it's working out the same. Okay.
Actually, I just kind of got curious and was messing with things. I put in the equation with minus 8/15 into an indefinite integral just to get the antiderivative equation.
Right.
And I did the same thing with the way Shelby did it, and they're the same graph.
This and this.
Yeah. Like the whole thing, I did an indefinite integral for both of them, and it's the same graph.
The whole thing.
To the Twilight.
Wait a second, I think I messed something up. Just a second. It may not be.
See, because I just don't see any way it can, because right here, this is going to be a. Yeah, I mean, those are two different slopes, so they got to be different graphs. One's got to go up with.
Maybe the laws of calculus just have ceased to apply in this room.
Could it be because the 40 and 80 are half? It's half.
Could the two graphs just like intersect at that point? And like they'd be different if you did part of the integral?
Well, that's what right here.
Yeah. Like for the antiderivative graphs like intersect at 75.
Now, what are we talking about here, Robbie? Are we talking about this?
Like or just like the antiderivative of the entire thing.
Of the entire thing? Of course, this part's going to be the same.
Yeah.
But, well, so the antiderivative, I'm not following you with the intersection.
Like if you graph the antiderivative, like could they just like keep just to 75?
Well, yeah, but then again, that's the 75 is in there. So I'm thinking if you changed it, then that would change. And then they would you know what I mean? I think maybe they would still. So maybe that would work all the time. I don't know. Brendan, you find something?
I'm still getting the same thing. Graph that I got from Shelby's
Did you do it on a calculator screen?
Yeah, I did these antiderivative first and then just copied them.
So 80 minus.
Well, that's how I did it, but it's the same, just distributed.
Because it would be 80. On mine, it would be 80. Yeah, 80. But see, wouldn't that be? Plus.
Oh, I think so.
So, because hers would be.
Yeah.
Oh, I'm just waiting on that.
Okay, and hers, so 80. See, because hers would actually be, because this times this is 40, so hers would actually be 40
Oh.
plus 8/15. and mine would be 80 minus. So. All right, anyway, well, let's move on.
I can tell you're not settled.
I'm not. I'm not.
Oh dang, I
But-
also made the rope longer, just to see
Oh.
if like, what
Yeah.
Brody was saying was weird, and I still got the same answer, so.
Well, I think the answer, I think the key is this right here. I think the key is this right here, where mine's the one in red, where the pounds are going down, right? And because hers ended up being positive, right? By putting a negative on there, you made that actually go up. So the X, but I think there's going to be this. I guess there'll be symmetry now. I just wonder if it has to do with where it stopped and started. And I guess it would, because if this is 80 and 40, and mine was gonna, yours started at 40 and ended at 80. Remember we said it was backwards? Started at 40, ended at 80. Mine started at 80, ended at 40. So there's gonna be that symmetry. And when you do the integral, then it'll still be that same area. I was thinking it would be negative. But the key here is we're letting x be two different things within the same interval, which I think, as a general practice, would be bad. That would be a bad thing to do. I think in this particular case, it's turning out to not matter. It's turning out to be okay.
If the initial and end values of both of them ended up being the same thing, would one of the integrals have to be like 75 to 0 or something?
Well, that's what I thought was going to happen. But see, that would make it negative. Both of these area values are going to be positive because we have this shift. We start up at 80, start at 40, so we start up above, so we're fine. But I think, well, if it's backward, I think this would work in this limited situation. I think that'll work. So if that made sense to you, and you want to keep doing it.
Well, the only
story
reason
short,
that I got to negative was because when I did like the slope calculation, it was 40 minus 80
Sure.
over 75 minus 0, which was negative.
And it's
So I just
negative.
left it.
The only time I would do that, the slope calculation to really make it work well, it would be to do this, is where I put the slope in front of an x and then I would add on what we started with, and that's how I would do that. Otherwise, if you're going to do it as the 75 minus x, I would make it positive because it'll end up negative when you distribute. That would be the best way. So I'm not promising it would work all the time, but it sure seems like it might. So, but I think it's more because of a opposite is switched, but the graphs are going to be positive, so when we flip them, we end up in the same area. I think that's what's going on. Okay. Okay. Moving on. So hopefully that added to our understanding of it and maybe didn't distract. Now, we said on pumping liquid, I'm only going to, bonus situation, that'd be about it. Okay, so I throw this up here, but again, you notice all the integrals for work, foot-pounds. Pounds times feet, we get the pounds from the spring equation. Pounds times feet, the dx of the feet, the pounds come from the bucket, the rope, the water. Okay, and we see how that works, and all the bucket rope problems will basically be that way. Then we have the pumping liquid, with a little different. We're gonna take this slice and we're gonna pump it up, usually over the top or however far. So what we need is pounds. The way we get pounds of the liquid is the density, which you'll have to be given in the problem, times the volume. The only type I'll give you would be a circular kind of slice. So the volume of a circular slice is pi r squared h. The problem in the book is number 6, I believe. 7? 6? 6. The radius was 5. Okay, so all the slices here would have a radius of 5. So the radius would be 5. The height is just the dy. So that takes care of all that. And then the feet part of it is how far does it have to pump. So we said that we would label this with a y. And if you were just going to pump it up to the top here, that in that problem was 10. So how far does it have to pump? It'd be 10 minus y. So the 10 minus y would go in here for number 6. So you'd have your density was 62.4. Your volume was pi times 5 squared times dy. And then how far it has to pump is the 10 minus y. That's how far that slice would pump. Now, for the A to B, they said the tank was half full. So what's your integral here? 0 to 5. Because this is not how far we have to pump it. This is where is the water that we have to pump. So the slices that we're going to pump are from 0 to 5. So that's why that goes 0 to 5. But this is 10 minus y because it's how far does each slice have to go. So this slice goes from there to there. That would be the 10 minus y. So that's where that comes in. But again, for the quiz, I wouldn't worry so much about this one. We want to be able to dial in more on those two there. Okay, let's move on. The last thing, the last new thing we have to do is going to be involving differential equations. So if you want to get your notes out, we will talk about that now. And I've put up here two differential equations that we were supposed to memorize. Now, you don't have to write this down yet. Just write differential equations is fine for right now. Differential equations is fine. You don't need to write those other two. But I put those up there because those were two that we didn't know how to solve. So we just memorized their solution. But today we're going to learn how to solve them. All right. Now, in the other class, we were talking about college differential equation class. And what a college differential equation class is learning to recognize different types of differential equations and then how to solve them. Now, if you think about your high school math classes, that's been a big part of all of your high school math classes ever since Algebra 1. In Algebra 1, and probably before, you learned about linear equations. 3x plus 5 equals 7. When you see that, you know what to do to solve it. Take away 5, divide by 3, right? You know how to solve one of those. If I gave you x squared plus 10x plus 25 equals 0, a quadratic equation, how would you solve that? X squared plus 10x plus 25 equals 0. Factor it. How about quadratic formula? Right? But you recognize that as something different. That's not a linear equation. I can't get x by itself, so I have to do something different. So you learned about factoring, learned about quadratic equation. Okay, I was just helping an Algebra 2 student this morning who was doing cubics and fourth degrees, and they were doing synthetic division. You guys remember that? Some stuff with synthetic division is a way you can do other polynomials and try to solve those. Okay? Exponentials. If I give you e to the 2x equals 10 and tell you to solve that, what are you going to do? Log of both sides, right? Or turn it into a log, right? So all, and that took up the pre-calc. So and then trig class, right? You learned about solving trig equations. So at this point, you can look at different types of equations, and right away you recognize them as something, something that triggers something, hopefully, that there's a way or a technique for you to solve that. Well, that's what differential equation class is. You're going to learn all the different types of differential equations and what you need to do to solve them. Now, so far we have this. So far you don't need to write this down, but if I gave you this problem and asked you to solve this differential equation, what would you do? You would just do an antiderivative. First of all, the solution to a differential equation is what? The original function y, right? We want to get the original function. So you would recognize, what do you recognize about this that we can just do a straight antiderivative? Why can we do a straight antiderivative on that and we can't on this one? This has a y in it. If it's got the input variable only, like x, then we can do that. So see, we already can recognize that if it's one of these, we can just do a straight antiderivative. So we'd raise the power up 2, divide by 2, add on a plus c. And if I would have given you an initial condition like this maybe, then we could plug that in for the x and the y and we could find the c. So we had our general solution of the antiderivative. We have our specific solution. So we have already learned one method of solving a differential equation. It works on one that looks like that. However, on these two, since they have y's in them, we can't do that. So we memorize the solution. So today we're going to learn. Okay, so we're going to learn one technique, and that's the only other technique you're required to learn for the AP test. All right, but when you take a course in differential equations, you'll learn about other types of differential equations and what the ways of solving them. Okay, that's what that course is all about. All right, so what we're going to learn today is about separable differential equations. That's another group of differential equations. Now I've made a column here, yes and no. Yes is these are separable. We could use this method on these. The ones on the right are not separable. We cannot use this method on those. Okay? So if you want to jot them down, that's fine. If you want to just look at them here a second and see what they have in common and think about what it might be. But kind of like, you know, we learned, it's kind of like I might do with my Algebra 1B class. When we learned about solving quadratic equations, I might make a list of different equations and have them recognize, hey, can you use quadratic on this? Quadratic equation, is this a quadratic? Yes or no, kind of thing. Be able to recognize, right? And that's what we want to be able to do. Now, what do you notice is the difference in the two sides? What's one thing? You notice you got multiplication and division over on the left side, except for that last one. Okay? But what's different about the last one compared to the other ones over there? Oh, you know what? I just realized I have a mistake over here.
Yeah, there's no.
It's supposed to be an apostrophe.
No,
The capital E, because it's exactly possessive.
no, that is not what I was thinking of. But I have a mistake over here. Okay, that should have an X on it. Okay? Otherwise, that one would be no different than the bottom one on the left. Yeah, that was a mistake on my part. Okay, so now, what do you notice? That bottom one on the left is going to be okay. What's different about that and the other one? If you're adding or subtracting and they involve both x and y or t or y, whatever, the input and the output, that's no good. We can't do it. But if you have multiplication or division, or if the y minus 70, if it's adding or subtracting just a constant, then that's okay. All right? So it's separable differential equations. And the method we're going to use is called separating the variables, separation of variables. Okay, so this is one right here where we can do this. This is an okay one to do. Now the K just stands for any old number, but the reason I pulled that out is I wanted to show you that we will come out with that answer down there. Okay, so the first thing we're going to do in this method, and if you want to jot this down, is we want to rewrite the y prime as dy over dt. Now it could be dy over dx too. There's nothing in that equation, that original differential equation, that told me I had to use x or t as the input variable. Most of the time the problem will be given to you. A lot of them are written already in Leibniz notation, not with y prime, but like this, so then you know. All right, now, here's what this means. Well, the name kind of tells you what we're going to do. We're going to separate the variables. What we want is y's on one side, t's on the other side. So the first step is always this. The first step is always multiply the dt over to this side. So we get dy equals ky dt. So right away we separate and get the y's on the left side, the t's or the x's on the other side. Always that way at the beginning. All right, now you can see why then that would have caused a problem back in this batch over here. Because if I would have taken this first one and wrote that as dy over dt, or no, it'd have to be x, I guess, since I have x in there, and then had x plus y, if I would have separated that, now all of a sudden I'd have parentheses there, and there would be no way that I could get the y's together and the x's together, because no matter what I try to do, if I distribute or whatever, you can do all the algebra you want here. There's no way to get the x's on one side, the y's on the other. You just can't do it. Okay, and so that's why none of these would work. All right, now, the next thing, I need this y out of there. Now, the constant could be either place, but remember, what are we going to try to do at the end? In the end, we want to get what? Y by itself, y equals, right? So there's no sense moving the constant over here to the y side, because I'm eventually going to try to get y by itself over there, and so I'm not going to want any constants over there, so we might as well leave those on this side. So I need to divide that y. Now, I never write it as a divide. I always like to write it as a fraction. That's going to make it easy. So the constant can be on either side, but let's leave it over on the right side with the input variable, because we're going to want to end up with y all by itself. All right, here's the key, and here's why we couldn't learn this earlier. Because once we get to this part, what's just begging to happen next when you got a dy and a dt there? An integral, right? What we're going to do is the integral of each side, or the antiderivative of each side. So we're going to do the indefinite integral, which just means do the antiderivative of both sides. So what is the antiderivative of 1 over y dy? Natural log of y. We should put absolute value. Now, normally, usually the absolute value doesn't matter. So vast majority of the time, it doesn't really matter here. But we'll go ahead and put it in. Now, normally you would stick a plus c on here. But remember, we're going to try to get y by itself. So when I do the antiderivative of this side, I get a plus c. Antiderivative of this side, I get a plus c. They're not necessarily the same c. So when I try to get the y by itself, I'll subtract that c over to the other side, and you take a constant over here minus some other constant. What do you got? Some other constant. So we'll go ahead when we do this, and we won't put a plus c on that side, but we will when we do this side. So what's the antiderivative of k? K times t, and then plus c. Because remember, k is just a number like 3. The antiderivative of 3 would be 3t. All right? So we get that. All right, next step. We want to get the y by itself. What do we do? This is an e, right? This is a base e. E raised to that equals the y. So the y, we don't care about the absolute value now because this will always be positive anyway. E to the kt plus c, that'll always be positive, so no problem. And so we have that.
I'm sorry, I didn't hear you when you said it, but why did we put the C on that side?
Because we could have put the plus c on both sides, but they're not the same c. So if we had a plus c here, when it came time to get the y by itself, we'd have to subtract it. And when you take this constant minus some other constant, it's just a constant anyway. So it's just some other c, so we do that. Okay? All right, now we get this. Now, you might normally think you're done. But if we go back to here, we say, wait, that's not what we had. So are those two really the same? Well, they are. If you would, we'll do this several times today, so you'll get that, it'll become just a habit. You can almost skip it. But wouldn't this be, whoops, wouldn't it be true that this would just be this right here? Think about that then. If you multiply two things with powers, what do you do with the powers? You add the power. So if I had this times this, that would just be e raised to this added together. So we can go in reverse. If we got a power that's added, we can split it like so. Now what's e raised to the c? That's just a number, right? E's just 2.718 raised to some constant. It's just some other constant. So this is nothing more than some constant, which we can call just c, and then we can stick that around in front. You could even change it to an a if you wanted to, or we can leave it a c, whatever. And so now we can see why this exponential growth differential equation, which we had dealt with before, does have this as its solution. So no longer do we have to memorize that. If we see it, we will just solve it, and there it'll be. Okay? All right, now, Newton's law of cooling. For this one, I would like you to get out your 2012 free response. Hopefully it's near the top. We had it out recently. 2012 free response problem number 5.
Don't do it, drink it in.
2012 free response number 5, and I believe it is a no calculator problem. Everybody find it? Talks about the rate at which a baby bird gains weight, and it gives us this differential equation. Now, I would put to you that this is a Newton's law of cooling. Now, to be honest, you would not have needed to recognize that. And you notice B is the output variable here, okay? But if you look at that, and then if I can come back to my notes here, doesn't it look like the same thing? This would be the B prime. This would be the 1/5. This would be the B, and the 100 would be here. Now I've got B, and the way I wrote it is B minus 100. Your problem says 100 minus B. Does that matter? If you reverse a subtraction, you're just factoring out a negative, right? So if I factor out a negative, this would switch to t minus y, and then k would just be negative as opposed to positive or vice versa. So either way, that's a Newton's law of cooling problem. It's just with this flipped around, and then that would be the difference on whether k is negative or positive, okay? So I would suggest that this is really a Newton's law of cooling. So when we solve this, we'll be like solving our Newton's law of cooling. All right, if you go down to part C, notice what it said. Now this again was the AP test 2 years ago. Part C says use separation of variables. They actually use the term. Now not always do they. If you go back to the 2011, let me show you this. We won't do it today. But if you go back to 3 years ago, they had problem number 5, a landfill waste problem, and look at their differential equation. Newton's law of cooling, okay? Except the K is positive, so it's actually a growth thing as opposed to a cooling is more of a decrease. But there it is. And down here they just said find the particular solution. They didn't say use the separation of variables, but that's the only thing you can use. It's the only other method you know how to do. So sometimes they'll put the term separation of variables in there. Sometimes they'll just say solve. Okay, so let's go ahead and do the 2012 one. We'll work it together. All right, so the differential equation was dB over dt equals 1/5. What was it? 100 minus b? Was that it? Now, I would also suggest to you that this is like the one I had in our list down here, right? It was like this, where we have y minus 70. Here we have 100 minus b. Now we also have a 1/5 out in front, but you'll see how they're similar here in a second. So if we come back to this, all right, so we need to separate this. Well, the first step is to move the dt over there. So we get 1/5, 100 minus b dt. Okay, so there's the separation of variables that we use. All right, now what? We want the b's on the left. So what should we do? Should we distribute here? You could. If you distributed there, you would have dB equals 20 minus 1/5 b dt, like so, right? Now, I would normally suggest not to do that, okay? Because what happened is I just put a constant on with the b, and I'm going to end up wanting to get b by itself, and so having a constant on the b is just more work probably I'm going to have to undo later anyway. But what would we do at this point? Come on now, we need to separate variables, which means we have the t's on this side, the b's on this side. Divide by this entire quantity. Now, go back to my list here that I had up here a second ago. That's what you would have done here. The dt would have come to this side. You would have had the thing as a quantity. You would have divided by the whole quantity, right? Same thing. Now, on our problem here, I'll be honest, that would have worked if you want to do that. I would suggest just divide by the 100 minus b. Leave the 1/5 over there, right? It doesn't matter. It's going to work the same either way, but I want to write it that way. Okay, because in the end, it's going to, all right, so we end up with that, and over here we end up with 1/5 dt, like that. So you just divide the 100 minus b over to the left side, but write it as a fraction is better. All right? The biggest difficulty we're going to have here, I'll be honest, is algebra. Right? The biggest difficulty is going to be losing negative signs or distributing and then not knowing what to do when you're trying to get the b by itself. Now, we also may have some difficulty with our integral because that's what's next, right? Once we get things separated, we do the integral of both sides. The antiderivative of both sides. All right? So, what do we get on this side? That is natural log. Now, we're not always going to get natural log. I just happened to pick 2 examples where we get natural log. We're going to do another example where you don't get that. Just because you have 1 over something doesn't mean it's natural log, right? It's like if I had 1 over x squared, that's not natural log because it's squared. Okay, but anyway, we get this, and on this side, what's the antiderivative of 1/5? 1/5 t plus c. You have to do the plus c right there, and only on that side. Okay, now what? Now it's that e business, right? So 100 minus b is equal to e raised to the 1/5 t plus c. Right? Now, hopefully we saw that one time. What are we going to do with this right here? We're going to split that. You wouldn't have to work this problem, but I think it's a good habit to be in. This, remember, splits into e to the 1/2 t times e to the c, right? And what's e to the c? Just some other c which would go out in front. So I would get in a habit of doing that whenever you have one of those problems like that. I think it's just easier to work with. All right, but we're not there yet, right? We got to get b by itself. So we could what? Add b over to this side and subtract that, and then I'm going to flip it all around. So basically it ends up being b equals 100 minus c e to the 1/5 t. Now, if I can, what was our memorized solution for Newton's law of cooling? It was y equals big T plus, isn't that what we ended up with? Our big T was the constant, was the 100 in here. Sure enough, there's the 100. We had plus, came out minus, that's okay. That would just be the difference in sign on the big C there. But, okay, so it did work out to be that. All right? But that's how we solve it. Now, we're not done because this one says they want us to put in this initial condition. So let's do that. So we put our 20 in here. We put our 0 in for t. 1/5 times 0 is 0. What's e to the 0? That's 1. So c has to be 8. So final answer is b equals 100 minus 80 e to the 1/5 t. And that would be what they would be looking for to find the particular solution to that differential equation, and it's using separation of variables. There's almost always, in the free response section, I told you that there's we talked about the big ideas that are usually in the 6 free response questions. One of the big ideas is differential equation. Generally, at some point in that problem, you have to solve that differential equation. And it's usually a separation of variables kind of thing. All right? Now, I'm going to let you try one here. You guys try that one right there. All right? Again, it's got multiplication in it. Should be able to separate those variables, work together, help each other out. And then we'll go back into one of our sample packets and find one of those. All right, now, let's see. Are we getting them separated okay? Any questions on separating them? Do you see that there is not a natural log in that? Right? What do you get on the y side? Before you do the integral. What do you have over there? Isn't there a y squared or no? It's a 1 over y squared. So you can't do natural log with that, right? Since it's squared, it's what? How do you write that to do an antiderivative? Y to the negative 2, right? Yes, that's how you have to do that. So let me show you here. Top secret here, can't show it all. But let's look at that part at least. So we got y prime equals xy squared. We write the y prime as dy over dx, because these are x's now, not t's, equals xy squared. We need to get that dx over to that. Now I did this all in one step. As you get better at this, you can just do the moving around all in one step. I'm going to move the dx over to that side. That always has to happen first. We never have a dx on the bottom or a dy on the bottom when we do these, right? So the first step is always the dx over to there, the dt. So the x is going to stay, but the y squared needs to go over here, so you do that. Now you do the integral, but you're right, we can't do that with y squared, so we write it y to the negative 2. Here we got x. So when we do that antiderivative, we raise it up 1, which is negative 1, divide by negative 1. And over here we get 1/2 x squared, and then put the plus c on that side. Now what? Well, you could, but I'd like to get y by itself first, because we're going to have to. I mean, right? I mean, our final answer has to have y by itself. You could put your initial condition in right now to find the c, but you're still going to have to manipulate this to get y by itself. Let's just do it now. So what do you do with that? What do you think? Any ideas?
Multiply y over to the other side and then divide.
So this is really like a y underneath. So if you multiply a y over here and divide by this whole thing, right? Now, I thought of it a little differently, but it's really the same idea. I had this as 1 over y, negative. So if this is 1 over y, then y's got to be just the reciprocal of that, right? So it ends up being the same no matter how you think about it. So if I do that, let me show that then. So I did it this way. I just wrote that negative 1 over y. I said, okay, well then the reciprocal of that would be this, but it'd be a negative 1. It'd be a negative of that. So I just put the negative on top. So I wrote it like that, right? And that'd be the same thing you had, right? Now, I'm okay with that as my final answer. Well, we still have to find c. But I'm okay if you have that fraction in there. Now, the only time that might not be good is if it was a multiple choice problem and you had to match it, right? So how could I get rid of that half? What do you mean by factor out?
So it would
Oh, okay.
1/2 times x squared plus 2c.
Yes, if you factor out a 1/2, then that would turn into a 2c, but then 2c is the same as just c, right? I mean, so you could do that. I was thinking just take top bottom times 2, which ends up being the same. Because you factor out a 1/2, then you're going to flip that up to the top and make it a 2, right? So I was thinking just multiply top and bottom times 2. If I multiply top and bottom times 2, I get negative 2 up here, and I get x squared plus 2c, same thing. And then 2c, I think, is perfectly legitimate. You could leave it, but I just wrote it as a c. And I made myself a little note, 2c is equal to c. You wouldn't have to write that little note, but I would just, a reminder there for you. What did I just do? Now, if you want to leave that 2c, I'm okay with that. You can leave it 2c, all right? But 2c is just a constant, so we could replace it with just c. So this would be a legitimate answer. And if it's a multiple choice, you might have to do that. You might have a 2c, and you're looking at the answers, and they just have a c. And you're like, what happened to the 2? Just so you understand what's going on. All right, so either of those would be okay answers. All right, now, we got to plug in our initial condition. Now, I know I didn't give you enough time. Maybe you're not that far yet. But all right, so I took this version. I took this version and put in my initial condition. So I put a 2 in for x, I put a 4 in for y. 2 squared is 4, 4 times a half is 2, I get 2 plus c on the bottom, like so. Now what do you do once you get to there? Multiply the 2 plus c over to here, right? You multiply it times 4, you get 8 plus 4c equals -1. Remember I said a little bit ago that the algebra is going to be the thing? I mean, when you get into one of these problems, you put in your initial condition, you got all this algebra to do, especially on the no calculator thing, so we got to be prepared for it. Take away 8, we get -9, divide by 4, so we get c equals -9/4. So for this particular version, my final answer would be, since c is -9/4, I go and put that back in there, it would look like that. It would be okay, and we're going to do that here in a second. Okay? So now, that was that version. Okay, now the other version. The other version I had, which was this. So now I put in my 2 and my 4. So I get 4 plus c down here. Now I multiply that over there, I get 16 plus 4c equals -2. I subtract 16, I get -18. I divide by 4, I get -18/4, which is -9/2. So my c is different, right? Because remember, we had that 2c, which we turned into a c, right? So my c actually comes out to be -9/2 this time. And so I put the -9/2 in there, and I get that. Okay? Well, once again, I got a fraction inside of a fraction. So I would be okay with you leaving that. And honestly, on a free response, these would be okay. Either one of those versions would be okay. All right? On the AP test, for our final, I'd be okay with that. However, we could clear out those fractions. Now, on this one, what could we do? We could multiply by, we could do what Callan was saying and factor out, or just multiply top and bottom by 4 on this one. So you'd end up with a 4 on top. You'd end up with a -4 on top. And if you multiply the bottom by 4, you get 2x squared. And here the 4's would cancel, you get -9. So you get 2x squared minus 9. On this one, you multiply top and bottom by 2. So you get -4 on top, you get 2x squared, and here the 2's would cancel, same thing. Right? So any of those three would be acceptable potential answers because they're all equal. They're all equivalent. They're all the same thing. All right? That is separation of variables. Starting with a differential equation that has a mixture maybe of x's and y's. Now our first two we didn't have a mixture, they just had y's in them. And so we did, we had to get those y's over to the other side. This one had x's and y's, so we kept the x's on the right side, kept the y's on the left side, and we got y by itself. Initial condition, plug in. That is called separation of variables. Okay? And that is a way to solve differential equations that have that look to them. All right, there you go. Congratulations. As somebody in the other class said, we now know everything. Okay? And then, and I said, well, I wish. And so he said, well, I mean, we have nothing left to learn. Well, okay, I wish that was true too. Hopefully it is. We now know everything, and there's nothing left to learn. Maybe relearn might be the better idea. But so the homework is, I know, time out. I'm sorry, but I think this would be valuable. Let's open up that sample 4. Do we have that out already? It's our latest one.
Late as in dead or
The latest
You would hurt his feelings.
packet we have. But you don't want to.
It's being recorded.
Yeah.
That is possible.
All right. This is sample 4, problem number 25. A few of you have asked me about it. And I think if you go back probably through sample 3. I think there was at least one of those in there. I don't know about the free response. We haven't talked much about that yet, but the free response might have had some too. But in the multiple choice, there's typically one of those as well. But if you read this, it says at each point on the curve, the slope of the curve is 2y over x. Well, what's another name for slope of the curve? It's another name for slope of the curve. Y prime. Or dy over dx. So what they just told you there is that y prime or dy over dx is equal to that. Right? Hopefully that looks familiar now. Now the question is this. Well, once we get y equals, once we solve this, right? Once we solve this as a y equals, we should be able to recognize what type of a curve it is. So why don't you go ahead and do that one. And then we'll check it, and then I'll give you the homework. Now again, I'm sorry, but one last thing. That 2, what are you going to do with that 2? Leave it, right? Leave it. There's no need to divide the 2 over to the other side, because then you're putting it on the y side, and you're going to want to get y by itself anyway. So you move the 2 over there, you're going to end up moving it back anyway. So I mean, you could do it; it'll work. But I think it's a good idea. And once again, I'm just, looking out for your best interest. All right, you have ln. You actually have ln's on both sides, don't you? Because you're going to get a 1 over y, you're going to get 1 over x. Well, actually, there's a 2 there, but the 2 you can just pull out, right? I mean, so it's still a natural log. Okay? And what do you do if you got natural log on both sides? Actually, it doesn't really matter. If you got natural log of y, you raise it e, right? Now, so I went ahead and went this far with it. Okay? I'm sorry if I'm rushing you on this, but we're going to divide the y over to here, and we're going to move the dx over to there, so the 2 over x stays, and so it's that, right? So 1 over y is ln y. Now, the absolute values on these problems rarely matter. They can, though, so we want to put them in. And the 2 is just like if you pull the 2 out in front, 1 over x, okay? Now remember, if that was x squared or y squared, that's different then, right? Then they're not natural law. All right, so we have this. So now we want to raise it to the e power. You got the 2 ln x plus c, but again, that, just like we've been talking about with that plus on the power, that just morphs into that. Okay? Now, you're looking at that and you're thinking, normally you could stop, but yet you're supposed to identify what it is, and that doesn't look like any of those things up there. So what's missing here? What am I missing? Whenever you have an e raised to an ln, man, a big red flag that, wait a minute, those cancel each other out, right? The e to the ln, the problem's the 2's in the way. What can I do with the 2? Put it right up in there. Now, once I put it up in there, x squared, of course, is always positive, so the bars don't really matter at that point, okay? And so we get the e to the ln x squared and e to the ln inverse cancel each other out. So this becomes just x squared. So it's some constant times x squared, which is a parabola.
A parabola.
A parabola, yes.
There was a problem I almost ran into with e to the 2 ln of x. At first, I just wasn't thinking about the problem. So, if you split those two up, like e to e squared
Oh.
plus times e to the ln, is that a bad thing?
So right here, yes. Yes. E to the 2 ln x, if I heard you correctly, you were wanting to split that into e squared times e to the ln x? That's a bad thing because that would be 2 plus ln x.
Oh,
You add the power. Yeah. So yes, we wouldn't. That would be a bad. That would be a bad thing. Yeah, we bring the 2 up there and then we go. All right. So that's an example. I think back in sample 3, there's probably another one. I'll look that up and find it, and we can maybe do it another day. So your homework then is to practice. I've got about 5 or 6 problems here of some separation of variables on your homework, which is the bottom, towards the bottom of the assignment sheet. It's these right here. So here's what it's going to be. I know some of you may be gone tomorrow. I will be, because the track meet, if we have it, even if we don't have it, this is what we will work on tomorrow. So 7-4 homework. This is separation of variables, problems. Tomorrow in class, we will be doing sample 4 packet. We've already hopefully done all we can do and have most of them done on 1 through 28, the multiple choice, the first multiple choice section. So tomorrow will be 29 through 45, the next multiple choice section, that's the calculator ones. And then the free response, 1 through 3, which I think might be the calculator ones, I'm not sure. And so for next week, basically that's what you should have done. Okay, so we're getting really close to having the sample 4 packet finished. On Tuesday, we will review all of our chapter 7 stuff, be talking about those things, and then take the quiz on Wednesday. Then we will, on Thursday, let me see if I got this right. Yes, on Thursday, then we will talk about these, see what questions we have. We may start on a sample 5 packet, be working through some of that, but then on Friday we will do our first final. So this would be, this 4-day break, and whatever, there would be a valid time to be going back on those old packets, working things you don't have done, getting caught up with this. That's certainly our focus here as well.
Are we reviewing Tuesday? I might be gone on Tuesday.
Oh, yeah, you are probably, because I think the weather's supposed to be awfully decent. Then are you going to miss, was it Thursday of next week too? Which are just our review days. You'll be here for the test days.
It's the most wonderful time of year.
Yeah, well, Tuesday, okay. Let me run that worksheet for you. There's a review worksheet that we'll be doing in class on volumes and stuff. And I'll also have, try to get a video up of that, but those things we just talked about earlier, I'll try to get that up on the